Hey, everybody. Welcome back to another episode of Behind the Cape. I'm data superhero Keith Belanger. Joining me, fellow data superhero Ian Whitestone. Thanks again, Ian, for joining us for part three of all
We
of this exciting stuff.
we can't stop.
No, we
To
can't.
part three of some uncapped number. The limit does not exist with
Exactly.
Snowflake optimization and fun things to talk about. So excited to be
Absolutely.
here.
So maybe let's start it off with a little bit of a recap of, what we've done so far in the prior parts and then what you're going to get into today.
Yeah. So a bit the last call we did this we had took a bit more thought because it was a couple months since we did the first session, but back then it was kind of a high level of Snowflake kind of billing model, how to think about cost optimization. We talked a bit about some of the native cost optimization functionality and or cost control functionality that Snowflake offers. So that was the first one. This second part has been originally supposed to be one episode that's turned into a three-part series on query optimization because there's just so much to unpack there. So the second session we did, for those who haven't caught the recording, good place to start if you're new to this. We covered a quick recap of Snowflake's architecture, but then really dived in on how that looks in terms of like a query, the life cycle of a query in Snowflake and kind of the different layers that passes through. And then we started to look at the query profile and talk about how to use that, how to interpret all the stats. If you want to pull up my screen, I kind of have the visual we ended off on. And so yeah, very kind of dense information packed visual and tool that Snowflake gives you. And the reason this is so important to understand is like this is your lens, your microscope into how Snowflake is actually executing your query and what's going on under the hood. So for most people, I'd say I want to caveat this discussion is, most of the time you don't need to go look at this thing, right? Like Snowflake, the reason Snowflake is so popular and everyone loves it is because it just works and it runs
Right.
things fast. This is kind of for like the maybe 5% of the time or 10% of the time where you're like, I want this thing to run faster, or maybe I want this thing to run cheaper. Often those things are correlated because Snowflake's a serverless, a pay for what you use billing model, which means the longer a query is running, it's keeping a warehouse up, and that can mean more cost. So you come into here when you're trying to do one of those two things: make something run faster, make something run cheaper. Oftentimes those achieve the same result. So it's important to have a good understanding of this. So that's what we kind of did in the last session. And one of the places we left off that is kind of the launch point for today's discussion is kind of at the bottom right here where we start, and even the top part where we looked at what are the different time components of a query, and this example, the query spending most of its time scanning data. And then we talked about partitions and pruning. So today we're going to dive all into that, talking about kind of what are micro-partitions, to give a bit of a background. How can you enable query pruning, which is like telling Snowflake to essentially ignore a bunch of files and skip over the reading and reduce the time on kind of remote disk. And then we'll talk about ways you can cluster your tables such that they can enable effective pruning. And the reason this is worthy of the next 27 minutes we have, and arguably longer, is like this is the number one optimization technique in my mind. And it's kind of a simple one in intuition, which is that the best way, the fastest way to process data is to not process it, right?
Exactly. Yep.
Which everyone's kind of looking for this trick of like, oh, if you just join it in this way, or write the statement first. And it's like, no, it's all like the name of the game is avoid data processing. So I think you gave this example as like, did you need to filter 10 years worth of data, or were you really just looking for a recent sample? Could you've added a filter?
Right.
Example of not processing data. Everything we're going to talk about today with like query pruning and clustering is all about how do you not process data. So that's the game plan for today, is kind of diving into that and kind of going through these step by step. Does that sound good to you, Keith?
No, it does. And I, kind of have been there where people have this desire to like, I need to bring back all this data and then figure out of all that data I brought back what it was I needed, right? Versus just saying, just ask what you need, right?
Yeah.
You know, I
Exactly.
don't.
That's a good,
You,
yeah, that's a good
you,
way to
you,
think about it.
your eyes can't process a billion rows if all you're looking for is
Yeah.
five, right?
Yeah. Well, I got pretty good vision, Keith. So I would, no, I'm just kidding.
Yeah.
I have terrible vision. My glasses are over there on the table. Cool. All right, let's get into it. So I'll kind of just start running through some visuals, which I think are helpful to explain some of these concepts, and I'll let you kind of interrupt me whenever. So the first thing to understand is micro-partitions. So micro-partitions are the I said this on the last call. You can think of them as files. It's just a way Snowflake how Snowflake divides a table. So remember from before, tables in Snowflake live in the underlying storage layer of whatever cloud provider you're on. So we'll use AWS because it's a common one. And so we're talking files stored in S3. A table is just a collection of these micro partitions. So I've tried to illustrate that here with this diagram. Is you have a table, and you could imagine it like everyone. A table is easiest to visualize as a spreadsheet, right? And so that's what you kind of have here. And what we've shown, and this is like a gross simplification, but the first three rows get written to this first micro partition, and the next three rows get written to this next micro partition. And in red, apologies to the colorblind, and the third one gets written to this, or the next three rows, 7 through 9, get written to that third micro partition, and so on and so forth. So under the hood, Snowflake is kind of taking this table and chunking it up into each micro partition. Does that make sense?
It does. Yep.
And
And so
these
it's really
these are all
making
just,
sure you get those micro partitions organized the way you need to.
yeah, exactly. That's what we're gonna get to, and that's what clustering is all about. Is how do you kind of organize your data in the best way in these micro partitions? So I'll build up to that. But yeah, like this actually ties into kind of another thing I hadn't planned to talk about today, but the whole idea of you'll hear a lot of the time in the kind of Snowflake best practices that you want to avoid frequently updating tables, and you want to try and batch transactions together as much as possible. So an example of an anti-pattern is I'm going to write a query that updates one row at a time in a table, right? The reason that's an anti-pattern is easy to understand once you know how Snowflake stores stuff. So with micro-partitions, so each of these files, I said at the beginning this was a gross simplification because I said only three. There's like the first three rows, get written to the first table. The next three rows get to the first file. The next three rows get written to the next micro-partition. In reality, each of these they aim to keep them around 16 megabytes, heavily compressed. So uncompressed, like in memory, that could be like 250 megabytes. That means there could be like 100,000 records in one of these, like a lot of data stored, packed into one of these micro partitions. So don't let the name fool you there. And so that is the reason why you don't want to do single row updates very frequently, because every time you update a row, micro partitions are immutable. So
Right.
each time you do one of these DML operations, it has to add or remove the entire file. So if you're updating one record, remember you're actually updating 100,000 records each time you run that, right? So that's
Right.
why it gets really slow. Anyways, fun tangent. Hopefully helpful as a way to like think
No,
about
and it is a
why.
good. I know from my perspective, like on projects we were doing, like our rule of thumb was insert only, right?
Yeah.
It's faster you to handle the date logic than it is to do the update of an old record. So
Yep. Yep. Because update often involves like querying
yep,
that as well,
yep,
to find find the needle in the haystack.
yep.
So what's cool about what Snowflake does is, so for each of these micro partitions, for each of these files, they include a bunch of metadata. So if you can imagine, we show these columns, it's storing the number of distinct values, the min and max value of each column. That's all stored in the cloud services layer. And what happens is when you actually, I'll flip back to, I have all the slides here. When you run a query in Snowflake and the query optimization happens, there's this giant thing here I've shown, which is metadata storage. So at the time the query is being compiled and optimized, Snowflake can say, hey, for this table, which micro-partitions contain which range of files. And that's ultimately how you can enable clustering that's ultimately how you can get query pruning. So you can see here, let's look at this hypothetical example. I'm doing a select star from orders where created at is greater than this date, right? So in that step, in the cloud services layer, Snowflake will say, okay, which partitions contain which date ranges, and you can understand very quickly how it can use that information to eliminate partitions, right? In this example, I'm filtering anything after 814 because this data is magically sorted by created at descending. You can see that I actually only 814 starts here, and everything, all the partitions before that would include dates before it. So the query then only needs to read 3 micro-partitions. It needs to read these 3 at the top, and it can skip out even like it doesn't even have to look through all of those. Does that make sense?
Yes. Yep.
So that's kind of where that's why pruning is so powerful. That's why you should care about clustering, which we'll explain how to achieve in a second here. And Snowflake has continually improved their query engine to make pruning better and better. So, if we flash back to like 2015 when Snowflake was early on, like something like this probably wouldn't have worked, where you have you're doing a filter on this table and you're filtering at order date greater than, and you have a subquery that then selects a date and does some math on it. So I'm selecting a max and subtracting 6, and then I want to compare order date to that. Like pruning will also work for this today. And there's like a bunch of other examples I can give where Snowflake would just know exactly what you're trying to do and still apply pruning. So you'll find a bunch of cases where like it just works behind the scenes most of the time. It is important to call out, like there are scenarios where micro-partition pruning can fail. And I call this out because this is one of the important things. Like when you're debugging a query, you are going to be looking at the query profile. You're going to be saying like, what were the partitions scanned? What were the partitions total? And like, does that line up with my mental model of how many things should have been scanned, right? So a good way to think about this is like, I think this example was, filtering orders, right? And we filtered on a year. You should know in the back of your head, like roughly how many years of data are we talking about? And you should know roughly like how well is that data distributed? If you don't know, you can run a query and figure that out quite quickly. From there, you can then say, does this make sense that I'm scanning 491 out of 3242 queries? Does it make sense that I'm scanning 15% of the table, which I think is like a seventh roughly? So like, are there 7 years worth of data? If so, then this sounds correct. If not, right? If this was like 3242 or 1500, roughly half, that would tell me like something's up with pruning. Does that make sense? The kind of the mental model of like how to think about, is that working or is that not?
No, it makes a lot of sense, and being able to visually understand, okay, now I see what's going on behind the scenes.
Exactly. So there are cases where it can fail, and that's important. So as you look back on, like let's pretend that example, we are filtering a year of data. There were 10 years worth of data in the table. Like data is roughly distributed evenly across those years. And let's say our query was scanning like 75% of the micro-partitions. To me, something's clearly up. Either we've written our query in a way that Snowflake can interpret it and can't do the pruning, or the table is not clustered or has degraded cluster health. So that's kind of the fourth option I list here. So some examples where it can fail is if you have a function you apply on a predicate, right? So like here we're doing, pretty simple stuff, created at greater than this value. If I did some like complex transformation on created at and then filtered on a constant, it may not be able to prune as well. Because remember, like at runtime, at like query planning time, so before any executions happen, Snowflake's trying to make a decision in like 200 milliseconds or less. How should we execute this query? So it may not be able to like go and evaluate, oh, they're running this function on this column. The output of that function will be X, then go look up all the metadata. So it should go without saying, but this is like a very hard problem that some of the smartest people are working on trying to figure out, so you don't have to think about it. And in the meantime, until they figure out kind of all these edge cases, you should be aware of them. So one case where it can fail, applying functions on predicates. deeply nested views in general in Snowflake can screw up a lot of things with the query plan. So like if you're querying a view which under the hood queries 3 other views, and then each of those views, you can picture how this fans out, queries like 3 other tables. Like Snowflake has to go and kind of compile those views and then check, okay, which tables is this, or which views does this view query which table. All of that becomes very complex and can screw things up as the high level. So views are great. I would say use them wisely in terms of like complexity, the complexity of queries and the stacking you do. Because it tends to really throw things off in the optimizer for good reason. It makes the problem very tricky to evaluate. Does that make sense?
Yeah, it does. Yep. Yeah, and I've seen some, views on top of views on views that get very complex that you're almost as better off to write the query from scratch instead of doing
Yeah.
all those views.
Yeah,
Yep.
sometimes it's better to just blow things away
Yeah.
and restart. So yeah, like the big takeaway here with pruning is like the Snowflake engine is very good at often interpreting whatever you throw at it and then figuring out the best way to eliminate micro partitions based on that metadata that's stored. That's kind of like one of the takeaways. But there are cases where it can fail. So what do? Always check the query profile to make sure pruning is working. So we shared this already, but just to reiterate, you're looking at that partition scan partitions total. And you want to, if there's, this is one example, there's only one table in this example. If there were multiple tables, you kind of click on each of those and it will show you the relevant stats for each of those tables. Does that make sense?
It does. Yep. I
Cool.
think I think this also really demonstrates. I've had people ask me like, I don't understand why it's so fast to get so many rows and it takes a long time to get one row, right? If
Yeah.
if they're saying I want to go get order number 1, 2, 3, 4, 5, right? Well, we don't know which partition order 1, 2, 3, 4, 5 might be in, right? And
Yeah,
it's not
exactly.
right. The difference between a transactional type of database versus what Snowflake's doing here.
Yeah. Um, so yeah, like the reason they can be the same, just to iron that point home, is like if the table's not clustered in both scenarios, you have to scan all the
All
data
of
in order to find
exactly.
that answer. And like in this case, like data scanning is the most expensive part. It doesn't matter, like returning it and filtering it is really quick, but the scanning part, because of how Snowflake's designed with the separate storage and compute layers, just to go back here, is like you're kind of reading over the network. That is like orders of magnitude slower than like the very fast filtering group
Exactly.
by stuff that Snowflake can do on the warehouses themselves. So yeah, that's pruning. That explains why queries can run fast or slow. What's something we've kind of dodged at this point is clustering. So micro-partitions, just to recap, because there's a lot of terminology and I see people often get this confused. Micro-partitions are the files, like the underlying structure of the tables, Snowflake's proprietary format. Pruning is like the act of your or the ability of your query to eliminate micro-partitions and skip over them. Clustering is confusingly used in kind of 2 different areas in Snowflake. For the purpose of today, we're going to talk about table clustering, which is how do you get your table in a way that can enable effective pruning? How do you organize the data layout? We hinted at this earlier. The other kind of way this term can be used is with warehouse or computing clusters, which is like a different thing, a whole nother discussion on like multi-cluster warehouses. So hopefully that terminology is helpful. I think we should publish a cheat sheet on like Snowflake terms and
Yeah, there you
how
go.
to remember each of them. Cool. So this is kind of our definition of clustering, and both with the micro-partitions and the pruning stuff and like the stuff we're talking about here, we do have blog posts on both of these. So I will we'll share the links to those in the comments, I think, or the description. But what is clustering in our words? It describes the distribution of data across a table's micro-partition. So we would say that a table is well clustered if it has like a well clustered on a column, because that's important to remember, is like you're going to get well clustered on one or some subset of columns. You're never going to be able to like group together the same rows on all dimensions, right? On all attributes. It's just not possible unless there were like everything was perfectly correlated. So clustering you can think of as like for each micro-partition and for a single column, how similar is the data in that micro-partition, right? So with this one, we're talking about clustering on created at, like, do each of these micro-partitions, ideally, like perfect clustering would be they only contain a single date, right? Every record in each file contains a single date. This is possible once you have large enough volumes. For smaller tables, you may have like, a couple, like a week of September all living in the same file. All depends on your volumes.
Right.
So that's what clustering is. And like this, you need to have a well clustered table for pruning to work. Otherwise, it just won't work. There's a way you can check this, which I don't have in the slides, but if I go to Google, actually, can you see Google, or is it just showing?
I'm just showing your slides.
The slides.
Yeah.
Oh, darn. Okay, well, I will just describe it then. I was trying to switch tabs, but if you Google, what is it? It's a function in Snowflake. It's called like system $clustering depth or clustering information or something. You can pass it a table name and a column name, and it will tell you how well clustered is this table on those two things. So that will tell you, like, is that my issue? I'm trying to filter on date and it's just poorly clustered on that value. Maybe I'll follow up after as well. I'll include a link to that one in the comments as well for like, how do you actually check if my table is in a good state here? If it isn't, if it's not, there's kind of 3 ways your table can get clustered, can get into a well clustered state that are important to understand. So the first one is natural clustering. And you want to leverage this wherever possible because you have to do absolutely nothing to make it happen. It just happens. So I'll explain that in a second. Automatic clustering service is one that Snowflake offers out of the box, where you can tell it, I want you to keep this table clustered on this column always. And it just goes in the background and you never have to worry about it. The only downside of this service is cost. Like, Snowflake has to go out and do work for you. So it will cost you money because it costs Snowflake money to have services running in the background, constantly reorganizing the data in this table. The third method is manual sorting, which is often the most cost-effective option. So it's something that we recommend you try and use wherever possible, unless there are reasons you can't use it, which I can get into. So natural clustering is kind of the easiest one I mentioned because it just will happen. So a great example of this is, like, say you have an events table and you're kind of have an ETL process or a data loading process. It's like inserting records into this table. Let's call it every day. Okay. If you look at this, it's like, okay, here's a batch of 4 records. Of course, it'd be larger, but I'm inserting these on the 8th of, not the 8th, August 1st, 2021, right? And so they're going to get written to a micro-partition. And then the next day, this process kicks in again. And this time it has records from August 2nd and 3rd. So this table will be naturally clustered by created at, because the order that you're inserting the data into the table is like the data is like tightly bound by a range. Does that make sense?
It does. Yep.
So the reason I say this is the best one and you should embrace it wherever possible is because you don't have to do anything. It's just like I bet you, like, pretty much every Snowflake customer has at least one table where this is happening, because almost every Snowflake customer has some like event level data that they are kind of inserting every day. You don't always get that though, right? Like, you may have some process where you, maybe your data is inserted by created at, right? Like it's doing it based on the date the record's created, but there's some other column that you typically query on that you want to be able to prune on. So that's where automatic clustering comes in, is you have some other column that you want to cluster by, or say that the data isn't batched. Say that the data is loaded in bulk. The whole thing every day is like a new copy of the table is loaded. That's where automatic clustering can come in to say, I want you to go in and sort the data or like reorganize it by this column. Does that make sense?
It does. Yep. And
Cool.
and also, I like when I've been in some of those processes, right? When you're loading data in, is we're sorting that data on the way in. So trying to make sure that, hey, I don't know how that data is coming in from these files, but we're going to make sure that those events and those dates, right? Everything for that day is going in together, and that day is going in together. So those partitions are that data that's getting organized together.
Yeah. Can you hear the dogs barking in the
Yeah,
background, by the way?
the dog wanted to be part of the conversation today.
Okay,
So
yeah, just amped up about automatic clustering. No, it's probably a bird flew by and then they went off. So I apologize. I will if that continues, I will I don't know what I'll do. Maybe run upstairs and give them a little nudge to quiet down. Cool. So the last one is manual sorting, which is a way you can force essentially clustering. And that's where that, and so very quickly, essentially how you do this is you literally add an order by statement at the end. So this is like one of the best, like number one, I don't want to call it hacks, but like tips in Snowflake, because it's so simple. It's just sort the thing by this column. And then anything that queries on my cluster key will, and you're like actually filtering on that value on a specific range, will get pruning. And the way to visualize this is looking back at this table, which I kind of represented like a spreadsheet. This is ordered by, created at, and as a result, you can just think of like, imagine you have this giant spreadsheet and Snowflake's figuring out how to store this table. They're going to take the first chunk of rows, write them to one file, the next chunk of rows, write them to the next file. So it has to be ordered by that in order to get that kind of clean packing of the data in each file. So that is again kind of one of the great ways you can achieve this is just by doing this manual sorting. So those are kind of the three different ways you have to recap, and kind of like in my mind, the rules of thumbs are usually like try and use natural clustering if you can. If not, use manual sorting. And then if you can't do that, use the automatic clustering service.
great.
Does that make sense?
It does. That's always a wealth of valuable information. Greatly appreciate that.
Cool.
That's for sure.
How are we doing on time?
I think
Okay, we
we've
got
got
like a couple
a few
minutes
more
left.
minutes. Yeah.
Sweet. Well, let's keep powering through because I have some other kind of helpful tips. So one is like, how do you find good candidates for clustering? The thing you want to prioritize is columns that are frequently used in where clauses, right? So the only way you're going to be able to take advantage of clustering, or I should say the main way, is when someone filters on a specific range of data. If all of your queries running against a table are like select star from table, group by all, or whatever, like that's not really going to help you because the whole point of pruning is to eliminate scanning data. So if you have to scan all the data for your query, not going to be very valuable. So that's kind of part one. Part two is you need to pick columns that have a large enough number of distinct values to enable pruning on the table. So let's say your customer base was in North America. So there's like primarily, I think, 3 countries. I know like Central America may be included, but let's ignore that for now and use that as an example. It's like, if your column only has like a couple distinct values, and in this example, like say you had 2 distinct values, say it was Canada and the US, you will probably only actually terrible example because the US is 10 times the size of Canada. So if you filter on Canada, you'll actually get about 90% pruning, but pretend they're perfectly distributed. And if you have this column with two distinct values, you're only ever going to get like 50% pruning if there's an equal number of values or equal number of rows for each of those column values. So you want to pick something that has large enough number of distinct values. I'll just say straight up, like usually a date, some type of date or timestamp column is a very good candidate and a very common one because typically we're looking at like financial data. We're looking at orders over time for an e-commerce company. We're looking at events over time if we're, any other company, product analytics, security events, etc. And you're filtering on some timestamp. You often don't care about something that happened 3 years ago. You care about what happened last week or what happened over the last 3 months and how should we action that. So date and timestamp columns are often very good ones. And what you can do, and we'll publish it. We haven't done a blog post on this yet, but you can use the query history and the access history views to like look at your usage patterns on your tables and then figure out how should I then go and understand what those patterns are. Does that make sense?
It does. Yep.
When should you care about clustering your table? I will come back to my initial point, and maybe this is a good place to end, of like 95% of the time, maybe even 99% of the time, you won't need to look at the query profile. So we are sharing advice for the rare cases where you like want Snowflake to either run your query faster or run it cheaper. I would say a similar kind of rule applies with clustering. Most users don't need to consider this. Like, it just works, and you spending a bunch of time thinking about this won't actually be worth it to the business. You're better off thinking about business problems and not like technical problems. However, if you need to improve performance or reduce costs, clustering is a great technique. Why? Clustering enables better query pruning. Query pruning means less data has to be processed. Less data processed means faster query, and a faster query means lower cost. So that's kind of when you should care about it, and some of the other things that are important to consider. Maybe that's a good place to end. I think we're at 30 minutes.
Yeah, we'll bring us back. So that was, again, part 3 of a wealth of information. I think we're definitely going to have a part 4 to continue it on. But again, great information. I greatly appreciate you again joining me today. And we will, as you said, we'll put those comments, not comments, those links into the comments.
Yeah,
Share those tips for people. And again, thanks for joining me today, Ian. And we'll get ready for part 4, everybody.
looking forward to it.
All right.